Okay, so let's get cooking. Everybody online can hear me?
Yep.
All right, perfect. And as usual, if you have a question from the online group, just scream or something and that'll get my attention. One more check to see if anybody is in the waiting room. They're not. Okay, so let's finish up our last couple of slides from Unit 1. I already did put up the homework assignment, the very first homework assignment that we're going to do. It's a non-programming one since we really haven't gotten into that yet. It's this read a link thing. It's already on Blackboard, so you can go look it up on there. So read this web page and write a one-page paper summarizing the power and responsibility computer scientists has when wielding the power of modern computers, databases, and software. So it's a little one-page response to that. Should not take too long, but kind of gives you something to chew on relative to what this vocation has in store while we start getting into the programming, which will start today. Okay, and that is due on Tuesday. All right, so now if you remember, was there somebody who just had a question? Maybe not. Okay, so last time we spent our time talking about different ways of representing numbers, representing values, right? We looked at the different bases, binary, octal, things like that. And I mentioned that I would go through, you're kind of rushing at the end, looking at our shortcut for binary to hex and binary to octal and vice versa. So let's look at that again here. I'll just create a slide here called, I am sharing my screen already, right? I am not. Now I'm sharing my screen. Okay, so we'll call this the binary conversion shortcut. So this is why binary, octal, and hexadecimal are popular bases for computers. So binary is obvious. Zeros and ones, on, off, digital logic. So that's completely compatible with how computers work. All right, this on or off kind of idea. But now, representing things in octal versus representing things in hexadecimal, remind me, what are the legal octets in the octal alphabet? Okay, so 0 to 7. 0 to 7 are the legal octets. For hexadecimal, what are the legal hextets?
Wasn't it like 0 through 9 of letters?
Yep, 0 through 9, and what letters?
A, B, C, D,
E, F.
oh, yeah.
Should go, so it's 0 to 15. So hexadecimal is base 16. So it's 0 to 15, but we represent the 10 through 15 as A through F. Okay, so bottom line is hexadecimal, this is base 16. Legal digits are 0 to 15. Or legal hextets, sorry. Octal is base 8. And this is 0 to 7. All right, so we see any base, the legal values in the legal characters in its alphabet will be 0 to that base minus 1. All right, go ahead.
And then for the bits?
Yeah, for bits. Yeah, so binary is base 2. The legal bits are 0 and 1. All right, so if we have a value, so last time we looked at the, well, first let me kind of show it this way. Octal, the largest value in octal is a 7, correct? If you were to convert the value 7 from decimal to binary, what would the answer be? So create another slide here. 7 from decimal to binary. What's the pattern we use for converting a, so how do we convert 7 from decimal to binary? I see decimal and I see binary. Decimal's base 10, binary's base 2. We learned 2 patterns last class, right? Well, this is related to octal, but right now all we're doing is solving the problem of converting the number 7 from decimal to binary. So take 30 seconds and do that. That was the second pattern we learned last class, right? Converting a decimal number into its into another base. Okay, so 7 divided by 2. 2 goes into 7 3 times with a remainder of 1. 3 divided by 2. 2 goes into 3 1 time with a remainder of 1. 1 divided by 2. 2 goes into 1 0 times, so we know we're going to be done. 0 times 2 is 0 with a remainder of 1. We read our answer from bottom up, so this is 1 1 1. So now this guy is a binary number. So these are the bits that represent the decimal number 7. Okay, so we wouldn't call it 111 because that's something that is a decimal number, right? But this is actually a binary number. Sometimes you'll see binary numbers denoted with a little b at the end of it, but usually I'll just spell out saying this number is in binary. Because we do need to know, because right now if you look at this, technically that's illegal. That's basically a legal everything number, right? So it's legal in binary, base 3, base 4, base 5, blah, 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 so on and so forth. Okay, so you would have to know this is in binary. So that is the number 111 in binary. So that's the largest hexadecimal, I'm sorry, the largest octal value. This is the largest octal value. Fills all 3 bits in a 3-bit, call this a 3-bit space number. And what's the smallest octal value? 0. And if I was to represent the number 0 in 3 bits, what would the answer be? 3 zeros. 0, 0, 0. Now, realistically, I could just do it in single bit, right? Or single octet and just say 0. But if I'm saying we have a bit space of 3, so I got 3 characters to represent my number. My smallest octal value is 0, 0, 0. My largest is 1, 1, 1, and everything else is everything in between, right? So if I look at the entire octal, octets in binary, this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this is 0, 1, 2, 3, 4, 5, 6, 7. So we all agree that that is every single octet that belongs in the octal vocabulary, the octal alphabet. And they can be completely defined using 3 bits with nothing extra. I've literally done every permutation of 3 bits and fully described the octal alphabet. So what this ultimately means then, we'll just call this guy the octal shortcut. If I have the number 124 in octal, and I want to convert this to binary, I can do the longhand version of it and go from octal to decimal and then decimal to binary, because we've learned two patterns, right? So we know how to go from a base to decimal, and we know how to go from decimal to a base. So I can convert 124 octal from base 8 to decimal, following the first pattern we learned last time. Then I can go from that decimal version of that to the binary version of that using the second pattern we learned last class. It's doable, wouldn't be the end of the world, but it's kind of extra work, right? Or if I want to get octal directly to binary, I can just represent this as each one of these octets. So the octet 1, the octet 2, the octet 4, I can represent that as a 3-bit value. 0, 0, 1, 0, 1, 0, and 1, 0, 0. That is the binary version of the octal value 124. These first 3 bits is our 1, the second 3 bits is our 2, the third 3 bits is our 4. Go ahead.
Could you go back to the other slide for a second?
This guy?
Yeah.
Yep. And just like in a lot of math classes, keep in mind this is something that you could calculate too. It's not something you have to memorize. But get it down. But like I said, you also have the slides available on Blackboard. But if you were to go through and do the conversions, this is the value decimal 0. This is the value decimal 1, decimal 2, decimal 3. See how binary kind of counts. All right. So you see how there's this convenient shortcut from going between binary and octal? So this goes from octal to binary. Well, if I had some random, so let's go, let's say 1 0 1 1 1 0 1 1 that. So we have that number in binary to octal. We would split this guy up into groups of 3. Now we want to start at the right-hand side. So see how this last one actually only has a single octet in it? You could leave it like that. It's not the end of the world, or you can just pad it with 2 zeros. That doesn't change the magnitude of the value. 0 0 1 is the same as just 1. Start on the right. Because if you take any value, and this isn't like a trick, like we would never write it this way, but if I said 1024 in decimal, putting 0 1 0 2 4 does not change the value of that, right? It looks weird, but this is still a 4 in the ones place, a 2 in the tens place, a 0 in the hundreds place, and a 1 in the thousands place. I can put as many zeros out front here as I want. It's not going to change the value of that decimal number, what it means. All right, so we can always pad on the left, but the flip side is if I put a 0 on the right, that does change the value of that number, right? Now it's a much larger number. So always start your groupings from the right. That way you have your excess on the left and can just throw the zeros in front of it if that makes you happy. You don't have to do the 3-bit grouping if you don't want, because it'll still have its value, but if it makes you feel better to just always have groups of 3, throw the zeros in there to pad it. So now this is the octal version of this is a 1, this is a 3, this is a 5, this is a 3. So that's 1 3 5 3 in octal. And I promise you, if you took this number here and went and did that whole, I'm sorry, this number here, and went and did that whole breakdown where you converted it to decimal first, then converted it to octal, you'd come out with 1353. All right, so nice shortcut from going from binary to octal and octal to binary. Okay, so we see that that is the rationale behind why octal has become popular as a base for converting in computing, as opposed to base 9 or base 7, something like that. Because with 3 bits, we can fully describe the octal alphabet, but we can describe the base 7 alphabet, but then we have some extra unused bit groupings. And so we haven't been able to fully define it, so now this trick doesn't work. So the next step up, the next one we can fully define using 4 bits. How many unique ways can we represent 4 bits? So if I have 4 0 and 1s, how many different unique ways can I write 4 zeros and 1s? It's 2 to the 4th power, right? Which is 16. So 16 different ways, which just happens to be the exact same number of unique hextets that are in the hexadecimal character set. So we have 0 0 0, that's a 0, 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1, 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, and 1 1 1 1. Okay, and this is 0. Oh, I won't go. Well, just whatever. Let's just be complete. This is a 2. This is a 3, and you'll find that up to 7, these are identical to octal, right? Because I'm just counting in binary here. 4, 5, 6, 7. So now we're on to see how we had to start using the 4th bit now to keep going. So now we have our 8. We have our 9. Now this is a 10, but we represent it as an A in hexadecimal. This is an 11, we represent it as a B. This is a 12, we represent it as a C, D, E, and F. So we see that 4 bits can be used to fully articulate the hexadecimal hextets. Every one of them. No more, no less. The no less thing is the important part of that. Is if you have extra groupings of bits that are unused for a particular base, this trick doesn't work. Can everybody see the font here? You need to make it smaller. I can probably, here, let's just take the second half of this. Make smaller. Are you kidding me? Yeah, whatever. You can see all that, right? It's better. Go ahead. Yeah, that was so. That was brought up last time. I would say officially, it's always uppercase. but unofficially it doesn't matter. I think I was trying to come up with the name of some mobile app last time. Couldn't come up with that. They count in really large things, and they start, after they run out of letters in the alphabet, they start going AA, BB, CC, something like that. But generally speaking, in the world of computer science, you know, we're not anywhere near dealing with base 37 yet. So with that in mind, uppercase letters will suffice. But you're never going to like lose credit if you use in lowercase a. You will find examples that only use lowercase letters. It's not a deal breaker type thing. 4 bits. Yeah. So yeah, each one of these zeros and ones is a bit. So we have 4 bits represents the entire hexadecimal space. 6 bits would give us base 64, right? So so 5 bits. So if we're not using it yet, but the next level of this trick would be 5 bits, and 5 bits fully describes the base 32 set, whatever that alphabet's called. I'm sure it has a mathematical name, but I don't know what it is. Then if we go to 6 bits, that would be base 64. But then we have to start playing the game of, okay, we're out of letters in the alphabet. And we're way out of letters of the alphabet, actually, even if we go through twice. So that's when we have to start throwing in Klingon or making stuff up, that kind of stuff. But yeah, good news is we're nowhere near requiring that yet inside of computing. And chances are when we get to the point where we need to represent values that are that large, we'll probably be on to a new standard of computing. Like quantum computing or something like that, where maybe some of this stuff no longer is applicable. But we're pretty far away from that. Because we think about, you know, what's the purpose of representing values? You know, we don't have to get confused with computers here, because I mean, one of the things we're going to run into during your entire computer science education is right now, but for a while, you're going to be kind of intimidated by computers. Like, oh, these things are so complex. Why do they have to have all these zeros and ones? It's actually really easy stuff, just uncomfortable ways to represent that stuff. You know, if I told you to write down the number 17, you could all do it, right? Or write down the number 15, you could all do it. The second somebody says, oh, well, it's an F, technically that's right, but we're not comfortable with that, right? If you give me an F for a number for 15 and say, oh yeah, that's in base 16. I gave it to you in hexadecimal. You didn't tell me what base you wanted the answer in. You know, people would look at you weird, but it's technically a correct answer. You know, we've spent 17, 18, 19 years of our lives, some of you more, doing the human thing. 10 fingers, 10 toes, working with decimal. We're pretty comfortable with that. We're pretty comfortable talking to other people. You know, that's the whole reason why some of this stuff is kind of confusing, is because we haven't operated at this level before. But now we're having to try to understand kind of the language that the computer is comfortable with, and then figuring out how can we do that translation. But when we really think about what are the reasons we might represent values in computing, just real quick, I'll come back to that. Let me create a slide for it real quick. I just want to finish the example for hexadecimal. It's identical to octal. Why do we represent values in computing? Before that, we'll do our hex shortcut. So sometimes hexadecimal is just called hex. Base 16, all kind of the same thing. So my favorite hexadecimal value, BAD. If I wanted to convert that to hex, this is going to be, or to binary, a B is a 11. So that's going to be 1 in the 8th place. 1 in the, actually 0 in the 4's place, 1 in the 2's place, 1 in the 1's place. So that's an 11. A 10 is 1 in the 8th place, 0 in the 4's place, 1 in the 2's place, 0 in the 1's place. And a D is a, what is that, 14? 13. 13. So that's going to be 1 in the 8th place, 1 in the 4's place, 0 in the 2's place, 1 in the 1's place. So there is the binary version of BAD, 1011, 1010, 1101, without the spaces. And I'll write it again. Make sense? So nice shortcut, kind of why computers like these things. And like I said, if we went up to base 32, we'd have 5 bits to represent the entire alphabet for the base 32 numbering system, and same trick would apply. But we're not doing that yet for kind of the reason of the next slide. You know, when we think about computing, you know, what are the different things we represent values for? In real life, we use numerics to represent what, like our age, what year we were born, stuff like that, right? Those are the things that we use, or the decimal number system, to represent. So with computers, what things do we know that we use to represent values? Okay, so that's more of a mathy thing. Not that it's not a correct answer, but you know, let's just think, just like I said, for humans, it's age. What's kind of the equivalent of that in computers? Like maybe the amount of RAM you have? How much RAM do you have in your laptops? 8 gigs, 16 gigs? 8 gigabytes, something like that. What does that stuff mean? Bits versus bytes. I think I probably have this in the slide somewhere, but if not, we'll hit it here. So a bit is a 0 or a 1. That's a bit. Ooh. What's a byte? 8 bits. It's a grouping of 8 of those guys. That's a byte. All right. And I'll give you fair warning here. I'm going to try to trick you in a few minutes. I'm not quite there yet. So then from bit, we have something called a kilobit. So 1 little k b, 1 kilobit, is equal to 1024 bits. What comes after kilobit? One megabit is equal to 1024 kilobits. What comes after megabit? Gigabit, gigabit. That's where the trick is going to come in here. 1 gigabit is equal to 1024 megabits. And then we'll just cap it off at one where we're not quite there yet. 1 terabit is equal to 1024 gigabits. Then it would be petabits and exabits and things like that. Now, when we come over here to this side, this is 1 kilobyte is equal to 1024. This is 1 byte equals 8 bits. 1 kilobyte is equal to 1024 bytes. 1 megabyte is equal to 1024 kilobytes. Capital K. 1 gigabyte is equal to 1024 megabytes. 1 terabyte is equal to 1024 gigabytes. Make sense? So 1024 is our multiplier. And then to jump between the left and right column, it's either multiply by 8 or divide by 8. So divide, multiply. So question, how many of you have internet at home? How fast is our internet? Okay, 400 megabits, that's good. You see the commercials for internet. What do they say? We have 200 meg internet. It's kind of a, based on what you just learned here in this slide, it's kind of a misleading term, right? Is that megabits or is that megabytes? When they give you internet speeds, they give it to you in megabits. Why? It's a bigger number. Because 400 megabits is actually only 50 megabytes per second. Still pretty good. 50 megabytes a second is fine. You know, the lower tier of spectrum internet now is about 200 megabit. So it's 25 megabytes per second. All right. So this is kind of an example where, as a technology person, you should be able to see kind of how they take advantage of consumers. You know, next time you see a commercial that talks about the speed, they always say meg. On the screen, they might do the megabits with the lowercase m and lowercase b, but they don't say it. they give you a shorthand version when they say it out loud. Any of you have AT&T or Verizon, some like a telephone-based internet at home? You know what speed you have? Okay, so it's one of our goals as technologists is we should know everything about the technology that's around us, right? But in your defense, most students don't know what their internet speed is. But yeah, no, I get it. But you're a user of it, right? So at some point you can do a speed test, but which is faster, cable modems or what you have is DSL? So cable modems are substantially faster than DSL. So the fastest that you have at your house is 24 megabits per second. Chances are it's lower, it's probably 18 because you basically have to live at the phone company to get 24. Back in the early days of DSL, because DSL is based on how far you are from the phone company. It's called the digital subscriber line. And before they came out with this piece of network equipment called the D-SLAM, which basically was a repeater, you know, they just kept putting it like hops. And if they had installed one in your neighborhood, then you could get whatever speed was relative to your distance from the D-SLAM instead of the distance to the telephone company. But in the early days of DSL, like, you know, you were lucky to get like 128 kilobit per second. You know, that was like the speed of the internet, where 20 megabit per second was kind of the early cable modem speeds, which back then that was super fast. But DSL does have a just, it's not that AT&T doesn't want to give you as much, it's just their technology that they're using to deliver the internet just can't move the stuff as well. But now the telephone companies are going to be surpassing the cable companies because they're all moving to full fiber optics. So AT&T in downtown Milwaukee offers gigabit internet, which is, you know, 1,024. Well, if you take a 1,024 megabits is 1 gigabit. You divide that by 8, you have 128 megabytes per second of maximum download speed. Okay, so now if you sit on your computer and you try to download, you know, let's say you have a 400 megabit per second connection, which we said was 50 megabytes per second. Are you going to get 50 megabyte download? Why not? Go ahead. There's a possibility of that. I think most of our solid state drives today can keep up with that, but that's a good point. But probably not the thing I was thinking of. No. One thing that we see with our internet connections at home is your internet connection usually has 2 numbers associated with it. You have a download and you have an upload. And for consumer-based internet, your upload is much slower. So you might have 400 megabits down and you might have 25 megabits up. something like that. And what are you using your upload for? Like attaching Word documents to emails, making a request for, www.google.com, little small things. So your upload doesn't have to be as fast, right? But when you're downloading something over the internet, your download is related to whoever you're downloading it from's upload. So you could have the fastest internet connection in the world, but if you're downloading it from somebody who's on a dial-up modem from the 90s, the fastest you're going to get it is 5 kilobytes a second. That's what you're going to get it at. Go ahead.
What if it's like stored on OneDrive or like Google somewhere?
Well, so you take Google as an example. Might we assume that Google probably has more bandwidth than, Bob's internet provider or something like that? Yeah, so, but that doesn't mean that Google has unlimited bandwidth. So if you have a zillion different people who are downloading stuff from the same source, so Google has, a single file you're downloading somewhere, and we're rolling back a couple of years when this would have been a thing, and you have a whole bunch of people who are downloading it. Well, if every one of them is downloading at 400 megabits per second, you're going to have to take Google's total upload divided by 400 megabits, and that'll give you the maximum speed that the maximum people that can max out their connection over it. For those of you who have noticed in recent years, we've looked at a couple of different things to solve this problem, because when you have an internet connection, you buy 400 megabits, you want to get 400 megabits of use from it, right? Like, we might say as a internet user that 200 megabits is worse than 400 megabits. It's half as good. That's what it sounds like on paper, right? If you, how many of you watch Netflix in 4K? Or even normal Netflix? So normal net, most of us are watching Netflix, right? Or some kind of streaming service, right? Okay, so if we think about the data for that streaming service, you're watching high definition video, which is 1920 by 1080. So that's 100, oops, sorry. That's 2 million bits. So let's say HD TV. So this is 1024. I'm sorry, 1920 by 1080. And that came out to that number of bits. I'm sorry, actually, it's that number of pixels. That number of pixels. Okay, now by most of our current standards, each pixel is a dot of color that we might represent as 24 bits. Okay, so we might say at 24-bit color, this is kind of related to the stuff we've been talking about, we're using 24 unique bits to describe 2 to the 24th unique colors. So 16 million colors, 16.7 million colors. That's every one of our pixels on our TV can be one of those 16 million colors, where you have 200,000 shades of red, that kind of stuff. But we'll say it's 24-bit color. All right, so if we have 2 million pixels and we have 24 bits per pixel, that is this number. So 49 million bits per frame. Now, when you're watching TV, what's the typical frame rate? Okay, 60 is what your TV is capable of. Or if you get gaming monitors and stuff like that, it's like 120 or 144 for a gaming monitor. Go ahead. Yeah, usually it's 24 frames a second or 30 frames a second is a TV broadcast. When you're just watching TV, it doesn't necessarily need to be faster than that. If you're a gamer, You want as fastest refresh rate as you can get so that, you know, there's a smoothness to the game that you might miss. But if you're watching, you know, your favorite sitcom, you know, you're not worried about, you know, a dropped frame here and there or something like that. So, you know, let's operate off of 30. So we'll say 30 frames per second. So this is times that many bits. Gives us 1.492 billion bits per second. Okay, now we probably like to operate in the bytes world, right? So we'll come in here and we'll say we'll divide that by 8. So that's actually 186 million bytes. And if we want to get it into something a little bit more palatable, we'll divide that by 1024. That gets us kilobytes. Divided by 1024 gets us megabytes. So this is, or that many megabytes per second. So in order to watch regular high definition TV, this isn't even 4K. This is the crappy HD. You need to have an internet connection that can do 178 megabytes per second. So 178 times 8, so you need a 1,424 megabit per second connection. None of us have that. Only a couple of internet providers even offer gigabit yet, which is 1,024 megabits. So how do we watch streaming videos at home? We do that a lot, don't we? And you could do it with far less than the fastest internet out there. You know, you have AT&T's DSL, you're just fine. You can watch YouTube, you can watch 4K Hulu. You can watch 4K Hulu on that. How does it work? What happens? Go ahead. Okay. Okay. So one of the things he talked about, so my question here is, how do we watch streaming video with slower internet connections? And one of the things he mentioned is we buffer, right? We kind of catch up, load as much of it as we can until we can kind of keep up with whatever our connection is, so that we don't actually have to keep up in real time. We just kind of get ahead of it. Go ahead. Compression is the big thing. So if we were really to talk about Netflix's special sauce, it's their compression technologies. So even though we're saying this is uncompressed high definition video is 178 megabytes per second, uncompressed, our internet connections can't keep up with that. You know, and keep in mind that, you know, the internet bandwidth world works a lot like hotels, right? So when Spectrum or AT&T sells you 400 megabits per second circuits, they're really, really, really hoping that every single one of their customers isn't trying to maximize their internet connection at the same time, because there probably isn't enough bandwidth to maintain that. Kind of like how hotels will overbook rooms expecting a certain percentage of people not to show up, or how airlines overbook flights expecting a certain percentage not to show up. The idea here is they'll sell their bandwidth times 30% maybe. I'm making up that number, but they'll oversell their bandwidth with the hope that everybody isn't trying to use the maximum amount of their bandwidth at the same time. So compression is a technology that's used to reduce the amount of data that's actually being sent over the internet when you're streaming video. How many of you have some form of cable TV at home, or at some point in your life have had a form of cable TV or Dish Network or Direct TV, something like that? And you have this physical box, right? That sits above your TV or by your TV, whatever. You know, what does that box do? It decodes and decompresses. So because the data it's receiving is compressed data, it's also encoded data. It's encoded because they don't, Spectrum doesn't want you stealing cable from them. So, you can receive their signal if you just plug it into their thing, or if you point a satellite at the DirecTV satellite, you can get their signal, but it's encrypted. So unless you have the special code to unlock it, which there were people who hacked DirecTV boxes and stuff like that to do that, and they got all the channels, but they're doing two different levels of things there. One is compression and one is encryption for security. But the idea is that less data than you're ultimately going to be viewing is being sent over the air. That magic box is decompressing that and delivering a streaming signal to your television for you to actually see it. That makes sense? So this is kind of like, how do we play defense in the world of the internet? This is something that's easier today because we do have a lot more bandwidth today. And we roll back, we don't have to go back that far when bandwidth was a problem. In the early days of standard HD, so 720p or 1080i broadcast channels for HD, if you had a standard cable, one thing you might run into is sometimes you'd switch to one of the HD channels. Now all the channels are in HD, right? So this kind of has gone away. But if you switch to one of the switch to one of the HD channels, sometimes it would say, sorry, this channel isn't available right now, check back later. And the consumer's like, oh, they must be having a problem or something like that, right? The reality is that they can only actually, the way cable works is it's in pods in around a city. So like you and your, kind of your neighborhood are all sharing the same pod. And they might have only been able to send, they might only have the bandwidth to show 6 HD channels at once. So if you and your neighbors were both watching the same channel, then you lucked out because, they only have to broadcast that once. But if 6 people were already watching 6 different shows and you tried to watch a 7th one, you would be told that, oh, something's wrong, something didn't work because they didn't have a channel to send that on. So, we see some different things along those lines. But in any case, this is a real life example of data representation when we do think about how do we measure, when do we use these values, bits and bytes and megabits and gigabits and things like that. When do we apply these various number systems? So this is still base 10, but then we're further describing it. We might call this metadata and saying, well, this number is a measurement in megabytes per second. And that then has meaning to us. When we think about our computers, this is back to this slide, well, whatever it was. You can have it, yeah. So when we think about our computers, we think about the amount of RAM. So we have 8 gigabytes, 16 gigabytes, 32 gigabytes of system RAM. When we think about our hard drives, how big are hard drives today? So, you might have a 512 gigabyte, or you might have a 1 terabyte or a 2 terabyte, so on and so forth. Hard drive. Hard drives are long-term storage. System RAM is short-term storage. Those are things you'll be learning about in the 175 class. Okay, but in any case, from our perspective, we're thinking about number representation. We represent our system RAM in terms of we could give this in bits, right? In fact, Best Buy used to do that. Best Buy, when you had like 4 gigabyte hard drives in kind of the earlier days of larger hard drives, we don't think 4 gigabytes is very big today, but that used to be huge at one point in time. They may have said, okay, well, we'll say 4 gigabytes, we'll multiply that by 1024. Actually, what you do is we'll do that route. So 1024, that gets you actually in megabytes. That's 4096 megabytes times 1024 gets you it in kilobytes times, or kilobytes, times 1024 gets you it in bytes. Times 8 gives it to you in bits. So, and this is a true story. You might have seen on the shelf at Best Buy years ago that this is a 34,359,738,368 bit hard drive. That's just got to be huge. Just think about how many songs we can store in that thing. Okay, but everything has to do with this metadata that tells us what this measurement is in terms of. All right, that makes some sense? All right, so in our world of technology, we should be very familiar with this slide, bits versus bytes. That's something that's part of the lingo that technology people need to be able to speak. When somebody says, oh, this is a 3 gigabyte file, you need to kind of know what that means. If I asked, how long would it take to download a 3 gigabyte file over a 4 megabit per second internet connection? So something along these lines. So go ahead and take a couple minutes and try to solve that. How long would it take in seconds to download a 4 gigabyte file over a 400 megabit per second internet connection? All right, so let's take a look at this. One thing I'll throw out here, I mean, I kind of covered this over the first week, but I kind of mentioned that programming is hard, and obviously I'm throwing a lot of stuff at you, all this mathy stuff and things like that. One thing I do before the exams is I go through the slides and I kind of focus in. I say, this is what you should focus in on the exam. This is stuff that's more fluff. Not that it's unimportant, but something I'm not going to really test you over. But as an example, by the time you're a senior, you'll have mastered these things. There really is not an example of a Lippmann exam that doesn't have at least one conversion question in it. And that's not just in this class, that's as a senior. You will have 10% of the exam, all my exams have 10 questions on them. There will be at least one question that is, you know, convert some number from hexadecimal to octal or something like that. Or I'll give you something along these lines of, you know, something that deals with bits and bytes and gigabits and that kind of stuff. This is something that we should be very comfortable with as computer scientists, because this is the language of our trade, right? You know, whether you go into, you know, networking or something like that, and you're having to deal with, okay, well, I have a computer lab across campus that's going to have 15 students, you know, using it simultaneously. I need to make sure it has enough bandwidth, but I don't want that particular lab to steal bandwidth from the rest of campus, stuff like that. So these are things that you have to consider when you're dealing with it. You know, whereas I might go through and point out some of the stuff that we were talking, kind of the history of languages and stuff like that. I might say, hey, these are interesting. Keep this in mind. It's a foundation that we're building everything else on top of, but I'm not a big fan of testing over memorization. So I want to see applied type stuff. So my exams are not fill in the blank or anything like that, where you have to regurgitate 10 things. Every now and then there might be something like you're going to have to memorize the base hello world program in almost any language. That gives you the ability to always start writing code in that language right off the bat. Python hello world is one line, but so that one's not rough. But punchline is very little will you need to memorize. Question?
I don't know if I did it right, but I got 81.92
81.92
seconds.
seconds.
Yeah.
All right. You don't know if you did it right.
I'm not.
What's your confidence? 50% confidence? That's a coin flip. Anybody else get the same answer? All right, he did. Are you higher confident now? All right, so let's look at, and you can actually do this multiple different ways. We want to know how much time does it take to get a 4 gigabyte file. Now, one thing we can do is we can scale this internet connection speed up to gigabytes per second instead of megabits per second. So we can say 400 megabits per second equals how many gigabytes per second. So that would be 400 divided by 8 gets us over to the bytes side of things, right? And then we would divide that by 1024 to get us gigabytes per second. So the 400 megabits per second is equal to 50 megabytes per second. Or if I divide that by 1024, I'm at gigabytes per second. So this is how many gigabytes per second a 400 megabit internet connection is. So now I can take my 4 and I can divide it by that value, and I get 81.92 seconds. Make sense? But similarly, I could have gone the other direction. I could have said, okay, well, let's scale my 4 gigabytes into megabits, right? So I could have said, okay, I have 4 gigabytes. That is equal to, so times 8, that gets me gigabits. So that's 32 gigabits times 1024 is megabits divided by 400 is the number. So if I have this many megabits, 32,768, so that is megabits per second divided by 400 gets me 81.92 seconds as well. So kind of like chemistry or math classes you've had before, you need to be talking about the same stuff on both sides, and then you can do the math pretty easily. But you got to scale them up or down to make sure you're. That reminds me, I think it was this a couple minutes ago. I think it was in high school. And I always struggled with those word problems from the math classes. And I would lose interest during reading the book. Do they still do word problems? Man, I hated those. So I remember there was one, my dad still gives me a hard time about it, but I know it was something about apples and oranges. It might have even been junior high. I don't remember what it was, you know. So it was, I think it was, you have so many apples and so many, you know, pears or something like that. And I gave my answer in terms of oranges. It wasn't even one of the available fruits. I think I had the right number. It was the wrong fruit. I think he took off points too. That just seems like it's worth an LOL with like an exclamation point at the end of it. There's another time, I think this was like elementary school, I think, where, you know, they have like the day where like the parents can come visit. We had a spelling test. I fell asleep or I zoned out or something during this test, and then the teacher said, "Are you ready for the next one?" So I wrote down "ready" as was my word. I didn't do well on that test. It was a rough one. Yeah, so I probably would give you credit if you gave me the right number and in terms of oranges on an exam, just because you remembered this joke. Somebody can do that. All right. So kind of makes sense how we use these various numbers to represent things, just in our, not only in our real life with, you know, decimal typically, but also inside of computers in terms of binary or hexadecimal, or when we talk about transferring stuff between computers, we start thinking about it in terms of speed per second, just like miles per hour. For in your car, we're thinking about megabits per second or gigabits per second, something like that. Okay, so let's keep trucking here. So we already kind of talked about this because we went past the conversion stuff, then came back to the conversion stuff, right? So we've already talked about high level, low level, machine level, and the nature of the CPU. Yeah, go ahead.
So when they encrypt something, that could mean that they're taking hexadecimal. No, this is all about it.
Well, encrypting can mean all sorts of different things because there's all sorts of encryption algorithms. But whether it's represented in hex or binary doesn't matter. It's still the same values, right? Yeah, usually encryption is a matter of applying some sort of mathematical formula to the data that's reversible. For standard encryption, we have something called hashing, which is one way. So if you, so that's how a lot of the password things work. So if you, like, you know, a place is insecure if you ever said you want to, you know, you forgot your password and you click the button and then they email you your password, that's problematic. That would not be considered very good security because you don't want them to know your password either, right? So typically the way it works is they store a hashed version of your password. So the very first time you set your password, what they do is they put it through a hashing algorithm. Usually it's something called like MD5 is a popular one. And they store your hashed password. Well, when you have it hashed, you can't undo it. You can't reverse it. So it's a one-way encryption, one-way cipher. So then what you do is when you type in your password to authenticate, they hash that and compare the two hashes to each other, which means that technically, if you have a finite output with a hash, so let's say you were dealing with a 256-bit hash, that means there's 2 to the 256 unique passwords, right? Which is a lot, but that's not infinity. So it is possible to have 2 separate passwords that both hash to the identical value, which means that, I mean, we're talking low chances, but it is possible that you could type in, you would have to have their username and your password, and it might get you into somebody else's account because they happen to have a password that's different than yours, but hashes to the same value. I mean, we're talking really statistically, that is an unlikely scenario, but it's possible. Yeah.
So when I used to screw around with Java when I was a lot younger, I would see people log into my game and they would encrypt their password on my command prompt.
Mm-hmm.
On my server window, whatever you want to call it. But I had the source code. Was there a way that I could have viewed what the hash was?
Well, you could have seen what the algorithm was for a hash, but by definition, hashes aren't reversible.
Oh.
Yeah, I mean, that's the definition of a hash. It's a one-way cipher. Even if you know the algorithm, I mean, like I said, almost all of the modern day hashing things use MD5. So you could go and look up the MD5 algorithm. It's not going to do you a lick of good, because you can take a 7 gigabyte file and hash it to 256 bits. Or you can take a 3-character password and hash it to 256 bits. So since the output has nothing to do with the size of the input, you can't go back. You've lost substantial data in that transfer. So it's meant to compare the hashes later on for. Yeah, I mean it's impossible to reverse a hash. I mean, you can do a brute force attack and say, okay, well, I have a list of passwords. I have a list of hashed passwords. I know they've hashed it with MD5. So what I'm going to do is I'm going to make a zillion guesses at what their password is, and then run it through MD5, compare the hashes, and if I get a match, then I knew their password was elephant or something like that. So, I mean, it's a brute force type thing, but you're not undoing their hash. You're just guessing and comparing. I mean, it's the fact that you can have 4 trillion inputs and have it be a fixed output. There is not a direct map. Yeah, so it's a mathy thing. Yeah, it has nothing to do with direct translations. All right, so we looked at this guy already. We talked about compiled versus interpreted. I think so, where compiled is before runtime, we converted into the low-level code that runs on the CPU. Interpreted means at runtime, and Python is interpreted. Loosely typed versus strongly typed language. We'll kind of see this by example, but Python's a loosely typed language, and this has to do with when we deal with variables. So when I create a variable or I create my version of memory in a programming language, some languages like C, C++, Java, C#, these languages require us to dictate the kind of value that this bucket was meant to hold, okay? Whereas Python does not require us to do that. To give you a real life example of this, let's say that you go out to Target and you buy a container for that you're going to store under your store shoes under your bed, something like that. So it's one of those containers that meant to slide under the bed, and you're going to put shoes in it, right? And you put a little label on the outside that says shoes. Now you put the shoes in there, put it under the bed, then you decide, okay, these are old shoes, and I'm never going to wear them again. You dump them, and now you're going to use that container for something else. In Python, you'd be allowed to do that. Python says, oh, well, you bought the container. This container can hold all sorts of things. You happen to put shoes in there, but now you can put tax documents or something like that. In languages like Java, C, C++, or our strongly typed languages say, look, you put the shoe label on that, that bucket's earmarked for shoes. You're not going to store shoes anymore? No problem. Throw the bucket in the garbage can, run over to Target, buy a new bucket. You want to store something else. Okay, that's a strongly typed language, which tends to also be a compiled language. So those things go hand in hand with typically with speed that we may or may not care about because computers are really, really fast. So don't necessarily view that as better versus worse. So Python is loosely typed and interpreted, which means it is a slower language than a compiled language. It also, being loosely typed, even though Python is loosely typed, you will find that at the very least, all the examples you've seen from me, I won't use the same variable to store different kinds of things. So I think good programming practice is when you create a variable, even though Python doesn't make you dictate what you're going to put in there, you will self-police. And if you're going to store your age in that variable, that's all you'll put in there is numeric data as opposed to 5 minutes later putting your first name. So I would say with Python, you should choose not to reuse that shoe container for taxes. You should choose to throw it out and get a fresh container for holding your tax documents. But technically, Python will let you repurpose variables for other things, whereas our strongly typed languages like C, C++, Java, C#, Objective-C, Swift, these languages, as soon as you put that shoes sign on that container, that was all she wrote. You're storing shoes in there. All right, questions about that? Go ahead.
In the case of like Java, can't you like delete that variable and then rename it?
Well, you don't delete the variable. You can create a new variable. You could change the value that's in a variable, but it has to be the same kind of value. Yeah, so if I have a bucket that has shoes in it, I can dump those shoes out and put more shoes in. That's allowed. But I can't dump the shoes out and then put taxes in there. And in Java, you wouldn't delete the variable. Java has something called automatic garbage collection. So it cleans up variables you're not using anymore anyways. But you would just create a new variable and say, okay, I need to hold taxes. So I'm going to create a variable called my taxes. And that guy is going to hold tax stuff, whatever tax stuff looks like.
If I went up and I changed, like, say my taxes was a variable name, and then I was holding my taxes from 2012 in it, but then I went back up and deleted it, and like the tax from 2012, but taxes from 2014, and that was
You mean delete it in your code?
Yeah.
Well, then your code will break for your older taxes.
Well, yeah, but
yeah, you could rewrite the code and just change the variable name.
I just wanted to.
Yeah. But ultimately, what we're talking about here has nothing to do with the names of the variables. It's the types it's built to hold. We typically, in programming, we would always name the container. This is, my shoe container. Maybe give it a pet name like Tina or something like that. Okay, but in real life we don't do those things. But in computer programming, we name our variables, and typically you name your variables something that is meaningful for what it's going to hold. So you might have two different variables, one for 2014 taxes and one for 2015 taxes. So two different containers for holding your taxes. Let's leave it at that for now. Okay, so those are kind of at the high level, two different kinds of languages we're dealing with. One not necessarily being better or worse than the other. Strongly typed compiled languages are faster, but computers today are so fast that might not be that big of a benefit for a lot of the things we're doing with them. General purpose versus domain specific. I think I talked about this, right? Talked about like programming languages specifically built for, so most of our languages are general purpose. Python, Java, languages that you've heard of or you'll get jobs for are very likely to be general purpose languages. These are languages that are built to solve a large, any kind of problem that you can solve with a computer programming language. Then you have these domain specific languages, which are usually built on top of general purpose languages, and they might be used for like programming like dishwashers or something like that, where you change up a cycle or something, and you don't really need to be able to create Call of Duty on a toaster or something like that. So you're creating a very focused type of solution. And then we talk about object-oriented versus procedural. The telephone, that's like the pile of wires. Can I talk about that? Maybe not. All right, so let me just hit this guy here first in our final minute, and then we'll talk about, remind me, object-oriented versus procedural for the beginning of class next time, and then we'll start getting into the coding stuff right after that, because that's unit 2. This is the end of unit 1. But which type of language is the best? It depends what kind of thing you're doing. If you're making a video game, you probably want to be working with one of the compiled languages that are extra fast, because things need to be fast. For our top tier video games, if you're making Angry Birds, that our computers are fast enough. You can, they'll be able to convince you that you're getting 1,000,000 frames a second, no problem, with Angry Birds. But if you're thinking about, how did they make Call of Duty or something like that, that's going to be with a language like C++, a very fast, compiled, strongly typed programming language. But at the end of the day, it's which language is best for the job you're about to solve. Anymore, a lot of times, the languages that really become power tools for us are these interpreted languages, because they're so much easier to create. We get a lot more of them, which allows us to sometimes have interpreted loosely typed languages kind of like a Python that are very focused in on solving a very specific problem. A good example of that is like the language PHP, which was specifically designed for web stuff. So things that it's a general purpose language. You can do anything you want with it, but if you typically make web pages, and one of the things you do is you connect to databases pretty often, like a MySQL database, that's like one line of code in PHP. They make something that used to be a little bit complex, 5 or 6 different things. It takes one line of code and you're connected, because that's something you do often with webby stuff. Make sense? All right, questions, comments, concerns, bribes. All right, first homework assignment is up. 1-page paper, shouldn't take too long. Just get you into the swing of things, get you some points. Remember, your next Bible homework is due by midnight on Sunday. And I promise we will get to the beginning of programming next class, right here, elevator pitch. We're talking about variables and stuff, just a couple slides later. So we will be writing software next week. Sound good? So punchline, you might go back to the notes, make sure you have your version of Raspbian or some kind of version of Linux installed in your machine. Also go through the tutorial for GitHub, which is a link, I think, on one of the early slides in there because that's how you be turning your homework in. You'll see me do it in class when I upload examples, but get yourself familiar with it. Make sure you have the tool on your computer. Sound good? All right, see everybody on Tuesday. Questions from online folks? Oh, they're dropping like flies.
Hey, what's the point of like a loose variable language then? Like, why would you claim a variable? Where is an